everyone. So today we've got a linear algebra question. We've got this transformation T that goes from P1 to P3, which is, P1 is the space of all degree 1 or less polynomials. P3 is the set of all polynomials of degree 3 or less. The transformation T of P of T is defined to be T squared plus 1 times P of T. And you have two bases here that we're gonna refer to here, 1 minus T and 3 plus 4T, that's the basis for P1. And B prime, which is 3 minus T, 2T plus T squared, 5 plus T squared, and T cubed, which is a basis for P3. Okay, and you have this matrix, which is the matrix that represents the linear transformation with respect to the bases B to B prime. Minus 13, minus 4, minus 7, 0, 8, 3, minus 1, 4, reading that as rows. And what we're going to do is we're going to find T of 8 plus 6T using this matrix, okay? Now, the first thing you actually need to do is, and usually that's not going to be given to you, is you have to compute a coordinate vector, okay, for the argument that you're plugging into your transformation. So I have to compute the coordinate vector for 8 plus 6t, because 8 plus 6t is what I'm interested in taking the transformation. In order for me to work with this idea of working with that matrix, you have to work with the coordinate vector, okay? And the reason behind that is, this matrix that we're working with that represents the transformation is numerical, it's a bunch of numbers. So I gotta multiply it by numbers as well, okay? And the coordinate vector basically is equal to the constants that go in front of the basis vectors that give you the linear combination, okay? So C1 times 1 minus T plus C2 times 3 plus 4T. So you solve that, you make a system of equations, and you get the answer of 2, 2, okay? And then what you're going to do is this. Once you find that, you're going to take your matrix and T, B to B prime, and multiply that by that coordinate vector, so that 2, 2. And you get this result right here, minus 34, minus 14, 22, and 6, okay? So that is your result that you're going to use to form the vector. How do you form your vector? Well, you take each of these numbers, and these are the coefficients of linear combination. And those are the coefficients of the basis vectors in B prime here. So the 1 minus T, let's go back to see what it was, 3 minus T, 2T plus T squared, 5 plus T squared, and T cubed. So you would have minus 34 times 3 minus T, minus 14 times, sorry, I have to go back and look here, 2T plus T squared, plus 22 times 5 plus T squared, and then finally plus 6T cubed. And if you did all that, you would get the result of 8 plus 6T plus 8T squared plus 6T cubed. Okay, that's what you'd get out of that. And yeah, if you went ahead and computed this directly, T of 8 plus 6T by using the definition would be T squared plus 1 times 8 plus 6T. And if you FOIL that out, essentially you just get the same thing that I have written up here. So yeah, same result either way. So a lot of people ask me, well, you know, what's so great about this? It seems like my work was more work here actually, and can be, depends on the transformation. But if your transformation is rather complicated, and you have to compute a lot of things as well, your matrix might be a lot easier to work with. Sorry, your matrix might be a lot easier to work with. So that's one of the ideas behind this, is that yeah, the matrix might compute things a little easier, and there's easier things to work with as well with finding the coordinate vectors, and I got to get into that. But anyways, so that's how that would work. Other thing that I wanted to mention is people will often stop at this point right here and think they're done, but no. Remember, you have to compute your ideas, like you're using the matrix to help you compute the image of that vector. So if that vector that's going in is in P1 and that transformation takes it to P3, I need something out in P3. So, you get some numbers, you're not done yet. Okay, so that's the application of this. All right, well, thank you so much for your time. Appreciate it.